Hi everyone, my name is Audrey, and today I will be discussing a framework for data-driven modeling to estimate reproduction numbers of both airborne and vector-borne diseases. So to provide some context, effective management of infectious diseases relies on accurately understanding transmission dynamics, and central to this are the basic reproduction number and the effective reproduction number, which measure disease outbreaks and transmission trends. Traditionally, both metrics can be estimated using maximum likelihood. However, these conventional approaches fail to capture the nuances of vector-borne diseases, potentially limiting their accuracy in complex epidemiological settings. In this talk, I will first discuss our employment of maximum likelihood to accurately estimate both the basic and effective reproduction numbers for airborne diseases, and then I will discuss the development of a novel framework for vector-borne diseases. So, basic reproduction number, often referred to as R0, represents the total number of secondary cases infected by a primary case. Now, to estimate R0, we can follow the Poisson maximum likelihood estimation-based method, in which we assume the total number of secondary cases infected by primary cases follow a Poisson process. Now, to construct this problem, we require the incidence data, or the number of new cases over consecutive time units n, shown here. And we also require the distribution of generation time, which can be thought of as the time post-infection. And since the generation time is a non-observable phenomenon, we instead approximate it by the serial interval W, which we define as the time post-symptoms, and this follows a gamma distribution, shown here. Now, in order to actually estimate R0, we can maximize the log of our likelihood function for all cases combined. Similar to R0, the effective reproduction number, or RT, is the average number of secondary cases per one case at any given time. So this number will vary as an outbreak progresses and indicates real-time transmissibility. Effective control measures put in place affect the RT of a virus, and because of this correlation, RT heavily guides policymakers to design effective policies. Now, to construct our likelihood function, we can follow the same Poisson likelihood process as R0, except now we will consider tau, which is a time frame or window for which we assume RT to remain constant. With that, we get our modified likelihood function here. And again, we can maximize this to find RT. However, using a Bayesian framework with a gamma distributed prior for RT, we can say that the posterior distribution of RT is as follows here, where parameters A and B are the shape and scale parameters of the gamma distributed prior for RT. Now, using these frameworks, we can apply it to real case data. So on the left here, we can see unique data during an H1N1 outbreak from a university town that was collected for a whole fall semester of 2009. Now, to find R0, we can maximize the log of our likelihood function, and we estimate for this data R0 to be 1.06. And for RT, using the Bayesian statistical inference in a window tau of 7 days, we observe the following to the right, where we start to see a decreasing trend in RT after around day 13. Now, traditionally, these frameworks and methods to estimate R0 and RT are also used for vector-borne diseases, and as mentioned, these methods fail to capture nuances of indirect transmission of diseases via vectors. So vector-borne diseases involve transmission of disease between vectors and humans. So vectors infect humans, humans infect vectors. Now, because of this, our framework for R0 and RT should be altered. The next generation of cases for the disease now relies on the reproduction of vector to human, which we can denote by RVH, and the reproduction of human to vector, denoted by RHV. And again, because one relies on the other, the overall R0 is computed using a geometric sequence of both RVH and RHV. Now, how does this affect our current likelihood function we've been discussing? As we've just introduced, we should account for both RVH and RHV. We also note that the next generation of cases N will now depend on previous cases for both humans and the vectors. And lastly, the serial distribution W will also differ between the humans and vectors. So taking all this into account, we developed a new framework for the likelihood function for vector-borne diseases. And these modifications allow us to better capture the dynamic interactions between vectors and humans, affecting disease outbreaks and transmission trends, ultimately providing more targeted and effective disease control efforts. So if you'd like to learn more about this new framework and our real case implementation for vector-borne diseases, please come to my poster at the ACSESS event. Thank you.